All right, so if you watch the last two examples in the previous two videos, you'll notice that although the procedure for computing the singular value decomposition was the same in both cases, the amount of work you had to do sort of shifted depending on the size of the matrix. So for example, in the first example, we were dealing with a 2 by 3 matrix. And so that meant that when we found our singular value decomposition, the size of these matrices, U was a 2 by 2 matrix, sigma was a 2 by 3, and V was a 3 by 3. All right? So first we computed A transpose A. Then we found the eigenvalues of A transpose A. That gave us 3 eigenvalues. And then we found the eigenvectors of A transpose A. Now, finding the eigenvalues and eigenvectors of a 3 by 3 matrix is not the funnest. It's not the easiest thing to do. There's a little bit of work involved in that. However, when it came time to finding U, we already had 3 vectors to work with. And since we only needed 2 vectors to find the matrix U, we were just able to use the formula, we were just able to use our formula to find the U vectors, okay? And there was not really any extra work required to find the U matrix because we already had sort of plenty of vectors over here to work with, okay? On the other hand, in the second example, A was a 3 by 2 matrix. So now U was 3 by 3, sigma was 3 by 2, and V was 2 by 2. So now it was super easy. That's a transpose there. It was super easy to find the eigenvalues and eigenvectors of V. And in the last example, we actually got lucky and it was easier than in most cases. But even if we hadn't been given a diagonal matrix, finding the eigenvectors and eigenvalues of a 2 by 2 matrix is not so bad. However, then the problem becomes to find the matrix U, we only have 2 vectors to work with over here. And so we had to do a little bit of extra work to find that third vector. Okay, so on the one hand, it was sort of it was more work to sort of find the eigenvalues and eigenvectors here, but this part was quite easy. On the other hand, this part was quite easy, and it took more work to find U. Now, I should say that it is possible sometimes if your matrix has lots of 0 singular values, even if you have 3 vectors here, you might still have to do that extra work to find the 2 vectors you're looking for over here, if you have lots of 0 singular values. So it's not always going to be sort of easy to find the matrix U as long as you have enough vectors to work with. It does depend on the number of singular values. But the point kind of remains that you either sort of have lots of work to do over here, and then there's usually less work here, or there's less work here, and there's more work to do over here. And it kind of depends on how you like to work on these problems because of the following theorem. So the fact here says that if A is equal to U sigma V transpose is a singular value decomposition of A, then a singular value decomposition of A transpose can be obtained by just swapping the roles of U and V and taking the transpose of sigma. So what does this mean? Well, if you are, if going through those examples, you really liked this example and you really didn't like this example, or vice versa. Well, if you liked this example, but you're given a matrix like this, what you can do is you can take the transpose of this matrix. That's going to become a 2 by 3 matrix. Then you can find a singular value decomposition of that 2 by 3 matrix, which, because it's shaped the way you like, it'll sort of be easier, or at least the process you'll like a little bit better. And then once you've done that, take the U matrix you found and the V matrix you found and swap them, and then take the transpose of sigma. Okay, so if sort of the shape or size of the matrix is sort of not amenable to really, working really easily with it or whatever, you can always take the transpose and find a singular value decomposition of the transpose, as long as you remember to swap the U and V back in the end and take the transpose of sigma. So that's kind of a pro tip. There's a little bit more. I mean, you got to be thinking and remember to sort of swap things at the end and take the transpose at the end, but that is an option if you're interested in doing that. The final thing we're going to talk about in this section is what's called the outer product form of a singular value decomposition. Essentially, it's the same thing as the spectral decomposition that we saw, where if my singular values are sigma 1 through sigma r, these are the non-zero singular values, so I'm just taking the first r of them, then what I can do, if I know what my u vectors are and I know what my v vectors are, I can decompose the matrix A as sigma 1 times u1 v1 transpose, sigma 2 plus sigma 2 times u2 v2 transpose, and so on, all the way up to that last non-zero singular vector. That's called the outer product form of the singular value decomposition. And let's see an example of that right now. So let's find an outer product form of this singular value decomposition. Or sorry, let's find the outer product form of the singular value decomposition of this matrix. So this is a matrix we've seen before, and if you remember, sigma 1 for this matrix was rad 3, sigma 2 was 1, and sigma 3 was 0. So then, according to this outer product form of the singular value decomposition, my matrix A should be equal to A, or sigma 1 u1 v1 transpose plus sigma 2 u2 v2 transpose. And so if we plug these in, plugging in the things we found earlier, this is rad 3, 1 over rad 2, 1 over rad 2 times 2 over rad 6, 1 over rad 6, 1 over rad 6. Okay, so that's my u1 vector and my v1 transpose, plus sigma 2 is 1, and my u2 vector is negative 1 over rad 2, 1 over rad 2, times 0, negative 1 over rad 2, 1 over rad 2. Okay, and so when I multiply these out, I get rad 3 times and then my second term is this. Okay. Now the observation is that both of these matrices are actually rank 1 matrices. Okay. And so the point of what this outer product form is doing, and this is actually one of the sort of the most useful things about the singular value decomposition, is that it allows you to take a potentially complicated matrix and decompose it into simpler matrices of rank 1. Now, why might this be useful? Well, here's kind of the idea behind why this might be useful. Suppose you have a big matrix that's filled with like stock price data, or maybe it's filled with shopping data of customers for some business or whatever. It's a big matrix, and in general it's trying to capture trends and sort of large scale features of some information that you care about. But as with everything, there's always going to be some noise in your data, and there's always going to be some sort of perturbations or fluctuations in your data that are not really important. So what you do is you can take if your matrix is represented as if your data is represented in a big matrix, you can do this outer product form of your singular value decomposition, and it gives you a bunch of matrices that are really simple rank 1 pieces. Now, when you compute the singular values, you might find that, say, your sigma 1 is like 1003, and then that's like times u1 v1 transpose. Then maybe your next one is like 998 times u2 v2 transpose plus say 721 times u3 v3 transpose plus 0.01 plus 0.001 say U5, V5 transpose, okay? So each of these things is a simple rank 1 matrix. And by decomposing it in this way, you can notice that, hey, these pieces here, because they correspond to really small singular values, they're not actually contributing very much to the matrix A. And so chances are they sort of are just the noise in the data that are not sort of really features or trends that you want to capture. So what you can do is you can kind of ignore these parts, okay? And what that does is it gets rid of sort of the fluctuations or the error in your data, and it leaves you with sort of just the larger scale trends in your data. Okay, so this is something that's really widely used. It's related to what's called principal component analysis, which is a dimensionality reduction. There's sort of lots of different ways in which the singular value decomposition shows up, but it ends up being a very useful tool in data analysis and data science. I won't say too much more about that because I think I'm out of time, but that basically does it for the course. On Wednesday, we're going to have a review day. I'll be able to answer any questions you have. We'll get ready for the final. So hope you have had a great weekend, and we'll see you Wednesday.